Unit 2 Equations. Our first learning target in Unit 2 will be learning target 2A, solving equations. By the end of this lesson, you will be able to solve one-step, two-step, and multi-step equations, as well as solve equations with variables on both sides. And then in our next video, we'll talk about how do we model those to then a word problem scenario and solve those equations as well. And the last couple examples in this video, we'll talk about, well, what happens if I have an equation that is an identity, or what happens if there is no solution to an equation. So our first example says -7 equals b minus 3, and the instructions for all of these say solve the following. A couple goals and key points that we have on the side that I just want to continue to remind us about is when we're solving something, so when I have an equation I'm trying to solve for a variable, my goal is to combine like terms to isolate that given variable that we are solving for. And remember, since we're working with an equation now, we have to make sure we're keeping that equation balanced, meaning the equal sign stays balanced, so whatever I do to one side of the equation, I have to do to the other as well, so that equal sign continues to stay balanced. So in our first example, we have -7 equals b minus 3. We are trying to solve for our variable, which is b in this case. To isolate b, I need to move the -3 and get that to the other side. To do that, I would do the opposite operation, and I want to add 3. And if I add 3 to one side, I have to add 3 to the other side. So what that ends up giving me then on the right side, if I have -3 and I add 3 to that, they will cancel each other out, and I get 0. The b is still here, and I've now isolated the b, and on the left side, I end up with -4 equals our b value. Now for the first couple examples, I will do this kind of in-between step of adding or maybe subtracting, multiplying, or dividing, whatever that problem calls for, but then you're going to start to see that I'm not going to write this in-between step on the paper, but I'll still be talking through it out loud. So our second example says 4x equals 16, and I want to go ahead and isolate my variable in this case, which happens to be x. So why don't you guys pause the video right now and decide, well, what would you do to isolate that x? Okay, to get that x by itself, I have to get rid of the 4, and since the 4 is being multiplied to the x, I would then divide by 4, so the 4's can cancel out, and I just get left with x equals, and now to keep the equation balanced, whatever I do to the left side, I have to do to the right side as well. And so 16 divided by 4, we can reduce that down, and that would be equal to 4. And we have now solved it. If I wasn't able to simplify down on a division, I would want to reduce it to as small of a fraction as I can and take out any common factors. In example 3, it says 2x plus 3 equals 15. So in our first two examples, we only had to do one thing to get the variable by itself. Now in our third example, I have two things standing in the way of getting x by itself. I have the 2 that it's being multiplied to, and I have the 3 that's being added. And I want to go ahead and isolate this x. So the first thing I'm going to do is get rid of this 3 to the other side, and since I'm adding 3, I want to go ahead and subtract 3 so they cancel out, and I get 2x equals 15 minus 3 will give us 12. Now that was our first step. Our second step to get x by itself, I want to go ahead and remove the 2 and get rid of that guy to the other side, so I would divide through by 2 so that they cancel each other out, which would leave me with x equal to 6 then, to go ahead and solve that guy. Now in our fourth example, we also have a few things going on this time. So example 4 says x minus 7 all divided by 3 equals -12. So in example 3, I only had the x being multiplied to the 2 and the 3 was separate, which is why we first subtracted the 3 to the other side. In our fourth example, the 3, which is our kind of coefficient on our entire left side, is both dividing x and the -7. So I can't add the 7 over first because of the 3 is in the way. So the first thing I have to do is get rid of that 3 to the other side. So I'm going to go ahead and rewrite the example, And I want you guys to think about what could you do to the left side of the equation that would make the 3 cancel out. What we would want to do is go ahead and multiply by 3 on the left side, because by multiplying by 3, we're technically multiplying by 3 over 1, which allows me to cancel the 3 over the 3. But remember, whatever we do to one side, we have to do to the other. So I'll multiply the right side by 3 as well. On the left side, since the 3's cancel, I get x minus 7. And then on the right side, negative 12 times 3 will give me negative 36. To go ahead and finish this example out, my goal is still to isolate and solve for x, so I need to get the 7 to the other side. Since I'm subtracting 7, I'm going to go ahead and do the opposite, which would be adding 7, so that it will cancel out, and I get x equals negative 29 in this case. So although example 3 and example 4 are similar to each other because they were both two-step equations to solve, the order in which we did those really mattered, and it made it easier on us by making sure we're kind of working from the outside down towards the variable x itself. Let's look at example 5. So in example 5, we have this scalar out in front, or this coefficient out in front of our term, and the first thing we're going to want to do, although we're simplifying and trying to get x by itself, let's go ahead and distribute and use the distributive property to distribute the negative 8 to both terms, since negative 8 is multiplied to the entire quantity 2x minus 1. When we do that, I'll end up with negative 8 times 2x, which will give me negative 16x, and then a negative 8 times a negative 1 will give me positive 8, is going to be equal to 36. So we've now dealt with the distributive property, so I no longer have those parentheses, and now this looks similar to what example 3 actually looked like, where I have a coefficient times our x plus or minus a number equals another number. So to isolate that x, the first thing I want to do is subtract 8, and whatever I do to one side, I have to do to the other, so I end up with negative 16x equals 28. From here, I want to go ahead and continue to isolate for my x, so I want to divide through by negative 16 to get x by itself, and that will leave me with x equals negative 28 over 16. And the negative sign, although it was connected to the 16, now is connected to the entire fraction, so we typically write it up in the numerator. From here, I can't divide them perfectly, so 16 does not go into 28, but I can continue to reduce it down, and both 28 and 16 are divisible by 4, so when I divide both of those by 4 and cancel the common factor, I end up with negative 7 over 4 as our final answer for x. I want you guys to go ahead and try the next one on your own. So why don't you pause the video and try example 6 on your own first, and then we will check it together. Okay, let's go ahead and check example 6. So example 6 is similar to 5 because we have the parentheses in it, so we're probably going to need to distribute. But the trickier part about 6 is, well, I have this 3 in front, so I have 3 minus 4 times x plus 2 equals 10. It's really tempting to want to start combining the 3 and the negative 4, but I actually can't do that because the negative 4 is connected to this entire x plus 2 term that we have here. So 3 and negative 4 are actually not like terms because I have 3 as one term and then my other term is 4 times x plus 2. So before I can combine anything, the first thing I actually have to do is distribute that negative 4 so that I have terms instead of a product of two things. So when I do that, the 3 is going to stay untouched because it's not being multiplied in. So I get 3 minus 4x, and then negative 4 times positive 2 will give me negative 8, and then equals 10 has stayed unchanged. So our first step we always want to do is make sure we're distributing anything that is necessary so that then we can figure out, well, what are our like terms and how can I combine them? Our next step from here is on the left-hand side, I have a couple like terms. So on the left-hand side, both 3 and negative 8 are like terms, so I can go ahead and combine those. So I have 3 minus 8, And if you would prefer, we can rearrange these and go 3 minus 8 minus 4x equals 10 so that we can see those better. And we know that 3 minus 8 is equal to negative 5. So I get negative 5 minus 4x equals 10. Now from here, my goal is to, again, isolate this x and solve for our variable. To isolate this guy, the first thing I want to do is get rid of that negative 5 and move him to the other side. So when I do that, I want to add 5 to both sides. So I end up with negative 4x equals 15 since I added 5 to both sides. Then the last step to get our x by itself would be to divide through by negative 4. So I get x equals negative 15 over 4. Again, we want to make sure if we can reduce it down as much as we can, and in this case 15 and 4 have no common factors, so I cannot reduce that any further. This second step that I did of rearranging, which I'm drawing an arrow to right now, is helpful when you're first starting out, but if you don't feel like you need it because you could see that when I combine 3 and negative 8 I get negative 5, then there is no need to show that step if you are comfortable with it. I just wanted to show it just to make sure we can see how I can combine the like terms from there. Okay. Let's look at number 7. So on number 7 we have 5x plus 2 all divided by 2 equals 2x plus 14. So now we actually have an x in more than one place. So I have an x both on the left-hand side and on the right-hand side. So for me to be able to solve for x, it means I need to combine all of those x's together. As it stands right now though, I can't subtract the 2x over and combine it with the 5x because the entire left-hand side is divided through by 2. So the first thing I want to take care of is kind of getting rid of this division by 2 on the left-hand side. So I'm going to go ahead and rewrite the original problem. So I have 5x plus 2 divided by 2 equals 2x plus 14 just by rewriting it. And from here, I want you guys to think about, well, what could I do to the left-hand side, which means I'll also have to do it to the right-hand side, that will get rid of this 2 down here in the denominator. Well, I could go ahead and multiply, so I'm going to erase that arrow so it's not in our way. I could go ahead and multiply by 2, because technically I'm multiplying by 2 over 1 then, and then those 2's would be able to cancel from here, which means whatever I do to the left-hand side, I also have to do the right-hand side, so I'll multiply the right-hand side by 2 as well. On the left-hand side, because the 2's cancel, I end up with 5x plus 2. Then on the right-hand side, I'm going to go ahead and distribute because that 2 is being multiplied to both of these terms. So I get 2x times 2, which will give me 4x, plus 14 times 2, which will give me 28 from there. From here, this looks a lot better that I have no more parentheses, I have no more division, and I can go ahead and think about how can I combine these like terms. Well, my goal is to be able to get x by itself. So why don't I move the 4x over to the left-hand side? To do that, I would want to subtract the entire 4x term, and then whatever I do to the right, I have to do to the left. So I'm going to move over here to our second column. When I subtract 4x on the left-hand side, 5x minus 4x would actually just give me 1x, plus 2 is still there, equals, on the right-hand side, since I subtracted 4x, I have no more x's, and I just get left with 28. Now this 1x, I'm not going to continue to write the 1 in front of the x, because if we don't have a coefficient in front of a variable, we assume that it's our invisible 1 that we have there. So what I really have is x plus 2 equals 28, and then to get x by itself, I want to subtract 2 from both sides so that I get x equals 26. So I was able to isolate it. Now going back to our line here where I have no more division and no more parentheses, technically it would not matter if you decided to subtract 2 to both sides first and then subtract the 4x over to the left-hand side. If you prefer to do it in that order, that's completely fine as well, because here, no matter what I'm adding or subtracting, I can do those in either order from there, just making sure I'm combining the like terms correctly. All right, why don't you guys pause the video again and try example 8 on your own first. Okay, let's check example 8. So in example 8, it says 2 times the quantity 5x minus 1 equals 3 times the quantity x plus 11. So on this one, it kind of looks similar to our example 7. Again, I have an x that's on both the left side and the right side, so eventually I'm going to have to combine those like terms. But before I can do so, I have to deal with the parentheses that I have going on, which means I'll have to use the distributive property. So I'm going to distribute the 2 on the left-hand side. So 2 times 5x will give me 10x, and then 2 times negative 1 will give me negative 2. Then on the right side, we'll do the same thing and distribute the 3 to both terms. So I'll get 3x plus 33 then. Now from here, my goal is to combine like terms. I again have 2 places with that x, so I'm going to go ahead and move the 3x over to the left-hand side. So to do that, I would subtract 3x from both sides so that they cancel out completely on the right side. And I end up with 7x minus 2 equals 33. Then to get our x by itself in our next step, I want to go ahead and move that 2 to the right-hand side by adding 2. So I'm going to add 2 to both sides. So we get 7x equals 35 then. From here, I want to go ahead and continue to isolate and get x by itself. And the last thing I have to do is get rid of that 7. So I'm going to divide through by 7 and get x equals 35 over 7, which we know simplifies down to be 5. So our final answer then would be x equals 5. Let's do example 9. So example 9 says 5 equals 5m minus 23 plus 2m. So again, this is similar to our last two because I have a variable in more than one place. What makes example 9 different than 7 or 8 is that in this case, my 2 places that have a variable are actually on the same side. So I'm not going to like subtract 2 to the other side because I already have them on the same side together. So I want to go ahead in my first step here and combine like terms. So what that means is on the right side, I can go ahead and combine 5m and 2m together. So I'll get 5 equals now 7m, since 5m plus 2m will be 7m, and then minus 23 is still there because that is not a like term that I can combine with the 5m and the 2m. From here, I have now combined the m's together, but I still want to isolate this variable, so I'm going to go ahead and add 23 to the right side, which means I have to add 23 to the left side. So I end up with 28 equals 7m. And the last thing I got to do to get that m by itself, divide through by 7. So I'll get 28 over 7 equals m, which we know then m is going to be equal to 4 since I can reduce that fraction down. And there is our 9th example. So we've got a couple more here that we're still going to try. And actually, I'll leave example 9 for you guys up there. I would like you right now to try example 10 and example 11 on your own first. So pause the video and try both 10 and 11, and then we will check those together. Let's go ahead and check example 10. So example 10 is similar to example 9, so I have more than one place with an x. So I actually have 3 places this time. So I have a negative 6x on the left-hand side, a 2x, and a negative 10x on the right-hand side. Well, the first thing I want to do is similar to what we did in example 9 and combine anything on one side of the equal side that I can together. So on the right-hand side of the equal sign here, I can combine the 2x and the negative 10x. So the left side is going to stay unchanged, so I'll just have 10 minus 6x still equals, now on the right-hand side, 2x minus 10x will give me negative 8x plus 1, because I can combine those like terms, and 2 minus 10 will give me a negative 8. Now this looks similar to a prior example that we've seen, so I'm going to go ahead and combine the x's first, and I'm going to add 8x to both sides so that I'm getting my x's on the left-hand side. When I do that, I end up with 10 still plus 2x, since negative 6x plus 8x will give me positive 2x, equals, on the right-hand side, I'll get 1 since the 8x's ended up canceling each other out. My next step to get my x by itself, although I've combined it down to a single x, I've got to still isolate it, so I'm going to subtract 10 from both sides. So I get 2x on the left equals negative 9 by subtracting 10. The last thing I've got to do is divide through by that 2, so I get x is equal to negative 9 over 2, and I cannot reduce that fraction down anymore, so we are going to leave it. Okay, let's check example 10 or example 11. So in example 11 it says 10 minus 3 times the quantity 2x minus 1 equals 4x minus 3 plus x. There's a lot going on this one. Again, if I highlight all those x's, I've got 3 places with x's, which means I really first need to combine all those x's together. On the left-hand side, I also have parentheses, so I'm going to go ahead and distribute that negative 3 in my first step just to get rid of all those parentheses there. So on the left-hand side, we'll get 10 minus 6x, since negative 3 times 2x will give me negative 6x, and then plus 3, because I have that negative times the negative, so make sure you're distributing the negative sign with it. So I end up with plus 3 equals, on the right hand side, I'm just going to leave it unchanged for now. So I'll rewrite it, 4x minus 3 plus x. From here, my next step is going to be to combine any like terms on each side of the equation that I can. On the left side, I have 2 constants, the 10 and the positive 3, so I can go ahead and combine those like terms on the left hand side, and that will give me 13 minus 6x. Since 6x is not a like term with 10 and 3, I cannot combine those, but I can combine the 10 and the 3. On the right side, I have the 4x and the plus x that are like terms, so 4x plus 1 more x will give me 5x minus 3 from there. Now that I have combined like terms on each side, I can go ahead and move all the variables to, let's say, the left side, and then I'll move all my coefficients or my constants to the right side. To do that, I will subtract negative 5x from both sides, which will give me 13 minus 11x, since I have negative 6x minus 5x, equals negative 3. To get that x by itself, I want to subtract that 13 over, so I have negative 11x equals, because I'm subtracting 13, I'll get negative 16 on the right hand side. Last step, divide through by that negative 11, so I get negative 16 over negative 11. Now 16 over 11 cannot reduce down, but a negative divided by a negative is going to be a positive. So my final answer then will be x equals 16 over 11. So example 10 and 11 both have a lot going on in them, but if we take it one step at a time and just start by combining all the like terms on the left-hand side of the equals, I'll combine all the like terms on the right-hand side of the equals, and then start moving stuff from either side, it makes it a lot easier for us to handle each step individually. Why don't you guys go ahead and try example 12 on your own first and pause the video, and then we will check it together. Okay, let's check example 12. So example 12 is similar to the prior two because I again have multiple places with this x. So I've got 2 on the left, 1 on the right side. So the first thing I want to do is combine any like terms that I can on the left hand side. So on the left-hand side, negative 7x and 3x can get combined together, and negative 7 plus 3 will end up giving me negative 4x plus 12. Now on the right-hand side, I can go ahead and distribute and get rid of those parentheses. So I get negative 6x minus 12, making sure to take not only the 6, but also the negative sign as well. From here, I've simplified and combined like terms on each side, individually, and now it's time to move stuff from either side. So I'm going to go ahead and move the 6x to the other side by adding it. Since I have a negative, I got to do the opposite and add 6x to both sides. When I do that, I can combine like terms on the left, and I end up with positive 2x plus 12 equals negative 12. Then from here, I can go ahead and subtract the 12 from the left-hand side. So I'll get 2x equals negative 24 since I subtracted 12 from both sides. Last step, divide through by 2, and I get x equals negative 12 from there. Okay, we have 2 more examples that we are going to solve through. So let's start with example 13. So this looks a little bit more simplified from before since I'm back to only having 2 x's. So let's see how we do this one. Why don't you guys pause the video and try 13 on your own first. Okay, let's check 13. So there's nothing to combine on the left-hand side, so I'm going to go ahead and rewrite it because on the right-hand side I need to distribute that 2 to both sides. Not both sides, I'm sorry, distribute the 2 into the parentheses. So 2 times 5x will give me 10x, and then plus 2 times 6 will give me 12. So now I have 10x plus 12 equals 10x plus 12. Well, that's always true, because if I start combining like terms here and I, let's say, subtract the 12 to both sides, then I have 10x equals 10x, which is always true. So right now, I have a statement that is always going to be true. It does not matter what value of x is because all values of x will work. Let's check that theory. So if x is 1, that will work because 10 times 1 equals 10 times 1. If x is equal to negative 1,000, well, 10 times negative 1,000 is equal to 10 times negative 1,000. So all values of x will work, which means I no longer just get one solution. So for all prior 13 examples, we were able to get one value of x that made that equation true. Well, now I have an equation that any value of x will work, which means I actually have what we call infinitely many solutions. Because all values of x will work, so I get infinitely many solutions for this equation. Oop, it should say an n. There we go. Infinitely many solutions. So this is kind of the first example where we've seen where we don't always just get one answer. And in math, we're going to have cases where sometimes we get one answer, maybe you get 2, 3, 4, depending on the type of problem it is, or in this case, we got infinitely many solutions for this one. And that really goes back to the fact that we have the exact same thing on both the left and the right-hand side. So no matter what value of x I plug in here, 10 times a number is always the same thing as 10 times whatever number I plugged in. Okay, our last example will be example 14. Why don't you guys pause the video and try 14 on your own first, and then we'll check it. Okay, so example 14 says 9m minus 4 equals negative 3m plus 5 plus 12m. So I'm back to getting multiple m's, and I even have multiple m's on one side. So I'm going to go ahead and start by combining our like terms on the right-hand side. So on the left-hand side, I can't combine the 9m and the negative 4, so I'm going to go ahead and rewrite it. But on the right-hand side, negative 3m and positive 12m, I can add together, and I'll get 9m plus 5. Now from here, if I go to solve this, I want to move my variables and combine them, so I'm going to go ahead and subtract 9m. But when I do that, on the right-hand side, they cancel out. That's what I wanted. But on the left-hand side, they also cancel out. And I get left with negative 4 equals 5. Well, the last time I checked, negative 4 can never equal 5. This is never true. So this is kind of the opposite case that we got in example 13. In example 13, we got a statement or an equation that was always true. But now in example 14, we're getting a statement that's never true. So no matter what value of m I plug in example 14, this statement is never going to be true, which means I'm in the exact opposite boat now where I actually have no solution. Or, well, it's not plural, just no solution. So we can have cases in math where I don't actually get an answer. So the equation that I started with will never produce a solution for that variable because I'll get a statement like -4 equals 5, which we know is never true. So in this case, we would get no solution then. That is the beginning portion of Learning Target 2A, where we're focusing on solving lots of different types of equations that we're solving. We started with our one-step and our two-step equations. Those were our examples way back in the beginning, with examples 1 through 4. And then with example 5 and further, they started to become more complicated with more steps that we were doing. But remember, if we take it one step at a time and we really focus on let's simplify the left side as much as we can and simplify the right side as much as we can, then from there as I start moving stuff around, this will make this a lot nicer for us as we go through and we build up to harder and harder